Okay, let's go ahead and get started. So last time we were talking about functions of random variables, of course. And there, we talked in particular, one of the sort of standard examples that I did was the probability integral transformation. And I talked about how this could be useful for generating random draws. Like, for instance, if you were interested in writing a program where you wanted to simulate random draws from some distribution, that sort of using kind of the reverse of the probability integral transformation could be useful. And there seemed to be some demand for an example. So what I'm going to do, I'm not going to do exactly that, but I'm going to do an example that is quite related, and then we'll sort of talk about the relation in a second. Okay, so here is the example. And just sit tight. There will be a connection to the probability integral transformation example here. So suppose we start with a random variable x that has a uniform distribution on the unit interval, and we have some function. We're given this function or came up with this function that we want to use to transform x. Okay? So what is the distribution of this transformed random variable? Well, we know how to do this. Remember, we can figure out first what the CDF of y is, and we do that in steps. We sort of argue what it is in steps. And then once we have the CDF, then we take the derivative and we get the PDF, right? So let's do that. Oh, but first, note that the induced support of y is just the sort of non-negative real values. Yep.
Log 0 is undefined, right?
Pardon me?
Log 0 is undefined.
Yeah, so it doesn't actually matter too much because the probability at any particular point is equal to 0. So we don't have to worry too much about what happens at any particular point. But yeah. Okay. So the induced support is the following. Okay, and we'll use that in a second. Okay, so now let's go through step by step, figure out what the CDF of y is. So remember, we'll start with the definition of the CDF. And then we plug in this function that we have. So we plug in negative log of x over lambda and into the probability statement. We solve for x, okay, standard stuff. And then we don't actually have to do the integral. So most of the time at this point, what we do is we write down the PDF of x, and then we integrate over the relevant area defined by this probability statement. But we're going to take a shortcut today, and that's because x has a uniform distribution. And so the probability that x is uniform, 0, 1. The probability that x is greater than any number is just 1 minus that number. Okay, that's only because x has a uniform 0, 1 distribution. Okay, so when we're dealing with uniform random variables, we can often skip the step where we have to do the integral. Okay. Okay, so here's what we have. That's the induced support. That's the CDF of the new random variable. Okay. And so we just take the derivative to get the PDF. And here's what we get. Okay? Fine. Everything's standard. Does this distribution look familiar? So we've seen this at least a couple times this semester, I think. It might be familiar from other contexts. Exponential, exactly. Okay? So now, recall that I said that if you have a distribution and you want, say, you want the function that transforms a uniform 0, 1 to that distribution, what you do is you just take the inverse of the CDF and you use that function to transform the random variable. Okay? So now let's just go back, take a step back, take the inverse of the CDF that we found above, and let's see if it's the same function that we used to transform the random variable originally. Okay, so here's our CDF. And let's just find the inverse function, okay? So we're just writing x equals 1 minus e to the negative lambda y and solving for y, okay? And we do that in a couple steps. And then we plug in the capital X and y because this is now the function we're going to use to transform the random variable x, right? But that's not the same function that we used in the example. What's going on? Any thoughts about what's going on here?
X and 1 minus X is the same.
X and 1 minus X is
Are the same distribution.
same distribution, exactly. Okay? So when I said that you can take the inverse of the CDF and use that to transform a uniform 0, 1 random variable to get the distribution of or to get, you know, sort of the PDF of the random variable that had this, whose CDF you're using. Okay, when I said that, I didn't say that was unique. Okay? So in particular, there might be lots of different functions that are going to transform a uniform 0, 1 random variable into an exponential random variable. And these happen to be two of the functions. And in fact, if you, if you sort of look at the functions, you might be able to convince yourself that these are going to give you the same distribution if you use these two different functions to transform a uniform 0, 1 random variable. Why? Because 1 minus x, this random variable, is also going to have a uniform 0, 1 distribution. Okay? I didn't prove it, but it's probably not very hard to believe that that's true. Okay? And you can prove it if you want. Okay? Okay, so what's going on? Both of these functions work, and in particular, the reason why both of them work is that, as I said, if x is uniform 0, 1, 1 minus x is as well.